Alright guys, let's continue with another lecture on this time on section 7.2, the continuation to the previous video, which is 7.1. So in this section 7.2 we cover rational exponents. So how is this related to the previous section? Well, in the previous section first we get used to calculate square roots, cube roots, and then nth roots like for root, fifth root, etc., which will be useful, uh, very useful and required to understand this section 7.2 first, right? So in this section we are going to play between rational exponent and radical notation, right? So we're going to look at the first case, right? There's the expression. Okay, let's see. Okay, so the first case, the expression a to the 1 over n, right? So in this case, a is any number and n is an integer, right? An integer greater than 1, right? So we are going to go from radical notation back and forth and rational exponent. So what does it mean? In other words, so when we change, right, when we change from rational exponent, the denominator of the rational exponent will be exactly the same as the index of the radical, right? And as usual, keep in mind that if n, the index of the radical, is an even number and a is a negative number, then the quantity we want to evaluate, it's not a real number. Otherwise, we're good, all right? Okay, so let's look at a few examples. So we are given a few examples that have rational exponents. So our job is to write this using radical notation, right? So in this case, let's write first using radical notation. Okay, then if possible, evaluate the expression and round to the nearest hundred whenever necessary, right? If we don't, I'll show you what that is, okay? All right, so in this case, the first example, let's highlight the denominator of the exponent, right? The exponent is 1/2. It's 9 to the 1/2 power. In this case, the denominator is 2. That means the index of the radical will be 2, that is. And in this case, again, we would have written a 2 here, right? However, for the square root, it's not necessary to write that number 2, so we just leave it like this, right? Well, in this case, this is a nice number. We can simplify in this case, it's possible to evaluate whatever we get, right? In this case, the square root of 9 equals to 3. All right? And that's the final answer. For letter B, okay, we have the number 18, right, to the 1/5 power, all right? So let's see. In this case, right, in this case, we are going to write down the radical symbol, okay, 18 inside and the 5th root in this case, right? All right, so we are going to find the 5th root of 18. However, the question is there a number whose 5th power equals 18? Well, in this case, there's no way we can raise a number to the 5th power, really big power, and get a number as small as 18, right? In fact, it's going to be a decimal, right? And in this case, we use the calculator, right, to approximate this, and I'm going to round to two decimal places, right? 1.78. Okay, and this is final answer. All right, if you have questions about how to use your calculator when finding roots, I can help you out on one of those Zoom meetings. You will show me your calculator and I'll walk you through how to find those, right? In the meantime, let's keep going with the lecture and then we can spend the time with the calculator. All right, letter C. So in this case, the denominator of the exponent is 4. That means the index of the radical will be 4. Okay. So we're going to have this fourth root of x, all right? And that's what it is. That's all we do. We're just changing from rational exponent notation to radical notation. All right, be very, very careful with letters D and E, right? Notice the similarities between the two of them, right? However, notice for letter D, we have some quantity raised to the 1/7 power, whereas for letter E, it's only the letter X, right? So in this case, because it's, let me highlight that, the entire quantity 3x is raised to the 1/7. In this case, the index of the radical will be 7, all right? Okay, and then 3x underneath, all right? And that's final answer. Okay. But what about letter E as opposed to letter D? For letter E, notice there's no parenthesis around the 3x, right? In this case, it's only the variable x, which is raised to the 1/7 power. So what is going to happen in this case? The 3 remains outside times radical x, and the index of the radical in this case will be, again, the denominator of the rational exponent. In this case, 7. So 3 times the 7th root of x. All right. Okay, let's move on to the next page. All right, let's move on to the next page. And let's look at another expression. Right now, in this case, we have the expression a to the mn. So in this case, the rational exponent has a denominator other than 1, right? And in this case, it would be a good idea to look at this one, okay? When we have a to the mn, right? It is equivalent to say either the nth root of a to the m or the nth root of a, the whole thing raised to the m power. All right, how is this different? In fact, let me make a distinction here. This one is hard. This one is hard to do, right? As opposed to this one, it's going to be a whole lot nicer, right? This one is, how about green? This one is easy, easier, okay? Let me give you an example on the side just to show you how bad this really is, right? Okay, I'm gonna drag to the next part right here, okay? And I'm going to evaluate. Let me make something up. How about I'm gonna say, okay, 81. 81 raised to the what power? I'm gonna say to the 5/4. All right, to the 5/4. Okay, in accordance to the rule, right? I'm gonna write it up here, right? A to the m over n is going to be a to the m, right? Inside the radical of index n, right? Which is also the same, even better, of a, okay, whole thing to the m power. All right, I'm gonna do this let me do it the hard way first, okay? Okay, so one way is to write the number 81 to the 5th power, right? And then take the fourth root. All right. This is equivalent to say the fourth root of 81 to the fifth power. All right. Okay, the hard version. Let me go down here. The hard version. This will be, okay, 81 to the fifth power. See how this is going to be 81 raised to the fifth power. Using a calculator, this will be the fourth root, right, of 34, 86, 78, 44, 0, 1. See how big and ugly this number is? And then take the fourth root from there. So this is just too hard. I mean, it's doable. However, it looks complicated, especially if you don't have a calculator. So in this case, we are not going to do anything using calculator unless it's one of those numbers that do not have a perfect root. But numbers like this, imagine trying to do a fourth root. So there's no way. Instead, you know what? Let me change the numbers. Let me change the numbers to make this nicer, actually. I'm going to change that 5 into a 3 instead, all right? Okay, let me change that into a 3, 3 and 3, all right? Much better. So 81 to the third power, all right? It's a nicer number. The fourth root of 531, 441. And then try to take the fourth root of that number. Well, we can barely think of a number, for example, the square root of 25. On the top of our heads, well, it's 5 because 5 squared equals 25. The square root of 81, well, the square root of 81 is 9 because 9 squared is 81, right? And then the cube root of 8. The cube root of 8 is going to be 2 because 2 to the third power, or 2 cubed, will be 8. On the other hand, the cube root of 27 will be 3 because 3 to the third power, well, it's 27, and so on and so forth. However, fourth roots are not straightforward. Now, try to think of a number whose fourth power would give you 531,441. Well, just reading the number, I'm getting dizzy here, all right? And well, the idea to keep this simple, okay? So this is the hard way, okay? Let me denote it hard. And here I'm gonna go easy, the easy way, okay? So instead of raising the number 81 to the third power to get a huge number, okay, use the third version of this, right? Use the third version and evaluate this instead. To do that, in order to do that, well, evaluate the root first and then cube whatever we get, right? And then, so what are we going to get here? Well, so we can easily evaluate the fourth root of 81 because that's a nice number, right? That's 3, right? So that's 3. So inside of the parentheses, we get a 3 and we keep the power. But what is 3 cubed? 3 cubed. And then that's 27. All right. So that's why this is easier. And this is hard. So hard, why is this hard? The hard version, it is hard because we make a huge number, and then we try to make it small. We want to reduce that big number, right? Now, the easy version, right? It is easier. It is easier to make something small first, and then a bit bigger, right? That's why this is your way to go. Your way to go. Right? That's your way to go here. Okay, let's go back to the examples here. Okay, let's go back to the actual examples. Okay, on our lecture notes. Okay, so let's simplify each of the following. Okay, so let's see. Number one, write each expression using radical notation, right? Then evaluate the expression by hand whenever possible, which is what we're going to do. Okay, so again, in this case, the exponent is a rational quantity, right? So let's highlight the denominator. Highlighting the denominator because that's what is going to tell us what the denominator of what the index of the radical will be, in accordance to the rules that we have here, right? What I just highlighted, right? This rule, right? Now let's write this down using radical notation. So the index is 2. There's no need to write anything inside of the radical, right? I mean, outside of the radical, we don't need to write down these 2. Just keep it like this. It is understood that this is square root, and then write 4 cubed inside. Okay, as opposed to the example I showed you on the side of the paper, right? I did a little bit of exaggerated big number just to show you how bad this could be. However, in this case, we are going to raise 4 to the third power. That's going to give us a 64. But in that case, it's not that hard to take the square root. However, let's call this the hard guy. All right, let's do it the easier way. The easier way is to write the square root of 4 and then cube. All right, so evaluate the root inside, right? Evaluate this. This is going to be a 2, right? So this is going to give us 2 cubed, which is 8. All right, that's going to be the answer. Letter B. Okay, notice the negative sign. The negative sign will be carried every single step. At the end, we are going to end up with a negative answer, right, as a final answer. So let's write this using radical notation. Notice the index is 4, so that means the tiny number in the upper left corner of the radical symbol will be a 4, right? Okay, so negative 4th root of 16 to the third power. Again, let me highlight this. You don't want to raise this 16 to the third power to get a huge number and then try to find for a number whose fourth power is whatever huge number remains inside. You don't want to do that. This is going to take too long. So this is what we're going to do. This is going to be negative times the 4th root of 16, all right? And then raise the whole thing to the third power. So the quantity right here, right inside for the root of 16. The fourth root of 16 is the number whose fourth power equals 16. In this case, again, it turns out that it's a 2, right? So negative 2 to the third power. And what is 2 to the third power? Again, is 8, all right? Like the previous example. However, we have a negative sign in the front, so be careful, all right? Let's do another example, all right? For the next example, okay, how is letter C different from letter B? So in this case, notice the negative sign, it's being affected by the power as opposed to the previous example. So in this case, it's negative power because it's inside of the parentheses. It's being affected by the power, right? However, in this case, in letter B that I just highlighted the negative sign over there, it's not being affected by the power 3/4, right? So let's see how this works. Okay, let's write this down as, okay, let's identify the denominator of the rational expression, right? Of the rational exponent, rather. That's what I meant, rational exponent. So in this case, the denominator of the rational exponent is 3. That means the index of the radical is 3. And inside, I'm going to obtain a negative 27 raised to the second power, all right? Okay, again, you don't want to raise the number 27 to the second power. That is 27 times 27, which is the quantity I'm highlighting here. You don't want to do that and obtain a huge number. Let's do it the easy way. So that's a hard way. Let's use the other version of it. So the cube root of negative 27, raise that to the second power, all right? Now, the cube root of negative 27. Okay. In this case, notice the negative sign that remains inside, right, of the radical. In this case, because the index is odd, in this case we have a cube root, right? We can take the cube root of a negative number, and the cube root of negative 27 is the number whose third power equals 27. In this case, the number negative 3, right? So from here we get negative 3, okay? And that negative 3 gets raised to the second power, all right? So, and that's going to give us a 9. That gives us a 9. Positive 9. All right? Final answer. All right, let's look at another example. Let's look at letter D, all right? Letter D. Okay, so in this case, we have a fraction, right? We have a fraction inside of a rational exponent. Okay, so number 1, let's identify the denominator of the rational exponent. That's going to tell us the index of what the index of the radical will be. In this case, this will be a square root, all right? Square root of 1/9 to the third power, all right? Again, we don't need to write that number 2, right? We don't need it. Just the symbol of the radical symbol itself tells us this is square root. Or otherwise, if it's cube root, we'll write it down. If it's for root, like in the previous examples, B and C respectively, right? That for those we wrote the index explicitly, right? Okay, you don't want to write 9 to the third power. 9 times 9 is 81, and then 81 cubed. That's going to give us a really big number. Instead, we do the following. I'm going to do 1/9, and then, so first I do the square root of 1/9, right? Which I'm going to highlight. Highlight this guy right here, and I'm going to get 1/3, right? The square root of 1/9 is 1/3. Okay, and then what am I gonna get? So we're gonna get the following. We get 1/3, which is the result, and then raise it to the third power. All right, and then from here we do the following. We are going to raise 1 to the third power, and then 3 to the third power. 1 to any power is always 1. 3 to the third power is 27. All right, what about algebraic expressions like polynomials inside of parentheses whose exponents are going to be rational exponents? Yes, we're gonna have those, and we are going to work a lot with this in the further sections. For now, we are just going to have a little fun and play between rational exponent notation and radical notation. So let's see. Again, let's sorry about that. Let's identify the index of the denominator of the rational exponent. Again, the denominator of the rational exponent is going to tell us what the index of the radical will be, right? So this will be the fifth root of the quantity 4x minus 1 to the third power, right? And that's all we do. In this case, if we have an algebraic expression, there's nothing else to do. So this is, you can write it like this or the other way, right? Open parentheses, the fifth root of 4x minus 1, and then raise it to the third power. Okay, and then let me fix this, it's too small. Okay, so the fifth root 4x there you go, 4x minus 1 and the whole quantity cubed, right? Either way is fine. So when you write it as your final answer on Math Excel, you can write either way, either the one in green or the one in yellow, doesn't matter. So in this case, there's nothing else to simplify because this is an algebraic expression and not just a numerical quantity like examples A through D. All right, so number 3, the third topic for this section is it's basically an extension of what we do with this expression, right? So for the second topic, we work with positive power, positive rational powers, right? So in this case, we may have negative rational expressions, right? So yes. So let's highlight this. This is very important, right? And how do we simplify this? Okay, every time you have a negative rational exponent, write the whole expression in the denominator, right? So 1 divided by whatever number. Where is this coming from? So you might remember from your previous algebra course, right? Every time you have x to the negative 1 power equals 1 over x, right? Or, as another example, maybe, I don't know, maybe x to the negative 5, right? It's the same as saying 1 over x to the positive 5, right? Or even, I don't know, let me do another one. Let me make something up again. How about x to the negative 11 equals 1 over x to the 11th power, right? So different examples, different ways, right? So same idea gets extended in this case for expressions in which we have rational exponent. All we do is take care of the sign. If we have, like in this case, we are given an expression, right, in which the exponent is negative, right? So all we do is write the whole thing down here, right? This whole thing right here in the denominator of 1, right? So 1 over a to the n divided by n, right? So just change the sign of the power by sending it to the denominator. And as usual, the same restriction, right? Keep in mind that if the index of the radical is even and the quantity inside of the radical, then we're not going to have a real number. All right. Okay, so let's look at a couple of examples covering this. Okay. All right. Okay, so number one, as usual, write each expression in radical notation and then evaluate the expression by hand if possible. And in this case, for both examples that I have here, A and B, it will be possible to rewrite them, okay? Now, we have 16 to the negative 3/4, okay? So let's see, number one, let's turn the power into a positive power by writing this in the denominator, right? That is 1 over 16 raised to the 3/4 power, all right? And then we are going to proceed by doing exactly the same we did on the previous topic, okay? What are we going to do? We are going to identify the denominator, right, of the rational exponent first, and that's going to tell us what index of the radical will be. So in this case, we are going to have a fourth root of 16 to the third power, right? That under 1. Okay, and then what do we do from here? From here, we do the following. Again, keep in mind that this version is the hard one. Let's do it the easy way, right? Let's change the other notation to the fourth root of 16, right? And then raised to the third power, okay? Now, the quantity I'm going to highlight here, this is going to give us, okay, the fourth root of 16. In other words, what number to the fourth power will give us the number 16? In this case, that number is 2, all right? So we are going to have 2 to the third power, this power right here, right? The one that I'm highlighting here and there, right? That remains the same, right? So that's 2, oops, come on, the marker, yes. 2 to the third power. And 2 to the third power will be 8 in the denominator. 1/8 is our final answer to this exercise, all right? Let's do the second example, example B. For example B, we have the number negative 27 raised to the negative 2/3. So there's a couple of negative signs going on here. Number one, which negative sign do we take care first? The one in the exponent, right? Let's change that to positive by sending the whole quantity, including the parentheses and the negative sign inside of the parentheses, the whole thing down to the denominator. All right? So this will be negative 27 raised to the positive 2/3 power, right? The negative 2/3 turns into positive 2/3. The whole thing under 1. All right, from here the next step is to write this quantity, right? Let's focus only in the denominator, right? And work it as a problem from the previous topic, right? Which is changing that into radical form, right? However, let's identify the index of the radical. So the index of the radical again will be the denominator of the rational exponent. In this case, the number I just highlighted, right, which is a 3. So this is the cube root of negative 27 raised to the second power, right? And it looks like this is one we already did on the previous page, I believe, right? Let me check that. Yes, I believe we did that already, right? I'm not going to give you the answer just right away, so I'm going to work it as if we didn't do it, right? Again, keep in mind that this guy right here is All thing that one that I'm highlighting in green is hard to evaluate because you don't want to evaluate negative 27 to the second power to get a big number and then try to figure out a number whose third power equals that huge number. That's not practical to do. I mean, it's possible to, but it's not, but it's going to take you forever, right? So instead, I'm going to change notation. So the cube root of negative 27 and then raise that to the second power. All right. So let's see. This, let's find out what cube root of negative 27 is. In other words, what number raised to the third power would give me negative 27? This is negative 3. Okay. So I'm going to write 1 over negative 3 to the second power equals 1 over 9th. So 1/9 is our final answer. All right. All right, now we're going to do the opposite. So far for parts, for examples 3 and the previous page, which is 2, right? We were going from rational exponent notation and turning into radical, and if possible, whenever possible, simplify. Otherwise, just leave it like this. And this is what we're going to do for what we're going to do in example 4. We're going to go backwards, and now we're given radical notation, and in this case we are going to write it using rational exponents, right? So let's use rational exponents to write each radical expression, right? Okay, so number 1, okay, the way we did it on the previous topics, right? We were identifying the denominator of the rational exponent, which is going to become the index of the radical. In this case, we are going to identify the index of the radical, and now doing this backwards, that's going to turn into the denominator of the rational exponent. So what are we going to get? We are going to get x to the 3 over 7. That's all we have to do, no more, no less. I'm going to highlight this 7 just so you can see where the position of that 7 and where is that coming from, right? And where does it go to? All right. Letter B. For letter B, okay, number 1. Yes, we are going to have radical expressions in the denominator, so that's b to the, okay, what's the implied index here? Again, when we don't see any number, a tiny number in the upper corner of the radical symbol, it's understood to be a 2, right? And this is going to be 3/2, right? Which in this case, I'm going to highlight the 2. The 2 comes from the index of the radical, and that underneath a 1. But in this case, this is not where we finish. In this case, we need to write with negative exponents. Let me write this as b to the negative 3/2. Right? So that's what we do. Okay. So for letter C, number 1, let's identify the index of the radical. So the index of the radical is 5, right? So that means that's going to be the denominator of the rational exponent. So notice the parentheses. So we are going to have, we're going to be remaining with those parentheses, x minus 1 to the 2 divided by 5, right? Notice how this 5 becomes the denominator of the rational exponent, right? And be careful here, right? This is what you don't do. Don't. X minus 1 to the 2/5 is not equal to okay, don't do that, please. No. Okay, we don't do that, right? We can, in other words, we can't distribute the exponent over a sum or difference of terms, right? Okay, so keep that in mind. We don't do that. Same for letter D. All right. However, be very, very careful. All right. So we have the fourth root, right? That's going to be the denominator of the exponent, right? So a squared minus b squared, right? To the sum power over 4, right? But what is the numerator of the exponent in this case, right? Well, keep in mind that this a squared minus b squared is raised by an invisible 1 there, right? That invisible 1 there, it's going to be this 1 right here, all right? And do we do anything else from here? No, that's final answer. That's about it. And again, as well, do not distribute this. Don't distribute this as a squared to the 1/4 minus b squared to the 1/4. Don't do that, okay? We don't do that, okay? Again, we cannot distribute over powers, all right? All right, the next topic, using the rules of exponents, right, to simplify expressions that contain rational exponents, right? And in this case, we are going to use all the rules of exponents that you have been familiar with from previous courses, right? Very basic rules, right? And in this case, I brought them to you here. So to review all of them and see how we are going to use them all, right? So, as usual, okay, let me highlight as I explain each of them, right? So, when we multiply the same base, right, with different powers of each, all we do is add the exponents, right? That's what we do. When we have some quantity to a power and then to another power, what do? Multiply the powers together, all right? When we have the product of two quantities, like in letter C, raised to a power, what are we going to do? We are going to distribute the n over each of the powers, right? In this case, we can distribute the power only when we have a product, not a sum or a difference, like I explained on the previous exercises, right? Then, when we have a quantity like this, a quotient of two quantities raised to a power, right? What do? Distribute the power to each the numerator and the denominator to obtain what we have over here, a to the n divided by b to the n, okay? And then, just like letter A, right? Every time we have the quotient, so the quotient of two same bases raised to the two different powers, what do? Subtract the power. Subtract the power of the quantity in the denominator from that of the one in the numerator, right? So that's what we do here. Letter F. For letter F, what do? So there, letter F is given in two parts essentially. Every time you have a quantity to the negative power, write it as 1 to whatever quantity to that positive power. On the other hand, if you have that negative power in the denominator, move it to the numerator with positive power, right? That's like going back and forth, right? So let's see. What about when we have, this is a very interesting one. So what about when we have a rational quantity, right? A quotient. raised to a negative power. We can change that power, that negative power, into positive power, provided you flip, right, or write the reciprocal of the rational exponent inside of the parentheses. For example, let me make something up. Let's see, what if I have, I don't know, 3/5 raised to the negative fourth power. This is the same as saying, okay, let me erase everything. Okay, example, let me call it an example. So 3/5 raised to the negative fourth power. I can just change that power into a positive one, provided we flip the quantity, the rational quantity inside of the parentheses, right? Okay. Let me erase that part. And of course, a very general one, right? Any quantity raised to the 0 power equals 1. 3 to the 0 power is 1, x cubed to the 0 power, m to the 0 power is 1, all right? Any quantity to the 0 power is 1. Okay, let's look at the examples. Use the properties of exponents to simplify. Write results, all right? Okay. Use properties of exponents to simplify and write all results with only positive exponents, all right? What are we going to do here? Okay. In this case, let's look at the first example. And notice something interesting. Notice we have the same base b, right? It's the same quantity, and the operation implied between them is multiplication, right? So what are we going to do with the exponents? In accordance to the very first rule, right? We are going to add the exponents, right? That's the rule that we are going to use. Rule A, okay? All right, so this is what we do. We write b to the 1/3 plus 5/3. In this case, we do the operation implied in the exponent, and the nice thing about this, let me highlight it, the nice thing about these two fractions is that we have a common denominator, so we don't need to multiply denominators by missing factors to come up with a least common denominator, and so this is straightforward to do. So we add 1/3 plus 5/3, right? This will give us b to the 6/3, right? However, that 6/3 can reduce to lower terms, right? 6 divided by 3, this is the same as saying b squared. And that's about it. In fact, we don't end up with a rational exponent. It's a perfect integer. This is really nice, all right? Okay, letter B. Let's have a look at letter B. All right, so we have the quantity. Notice the base, right? The base is x, right? There we have a common base. However, the operation implied is multiplication again, all right? So we're multiplying the same base in accordance to the first property, right? We multiply the same base, we add the exponents, right? So that's what we do, just the same way as we did on letter A, all right? So this is what we do, x to the 1/2, and I'm gonna leave a space here for a reason, plus 1/3. The reason why I left this space right here is because notice the denominators, right? The denominators are not the same as opposed to the previous example, right? So in that case, I need to find a common denominator, the least common denominator, by multiplying by the missing factors. So 3 and 3 and 2 and 2, all right? So this is going to turn into x to the 3/6, oops, plus 2/6, right? So 3/6 plus 2/6 is going to give us a total of 5/6, right? And well, in the instructions, we are required to, the instructions tells us to write only positive exponents, right? However, how about we practice on write this using rational exponents, right? Using rational exponents, the index will be 6 because that's the denominator of the rational exponent, and x to the fifth remains inside. So either one. So this, whether to enter, to input this or that answer on your MyMathLab account will depend on the instructions. If they ask you to write result only with positive exponents, then this is your way to go. Otherwise, if it asks you to write using radical notation, then you will use the other version, right? So positive exponents, and this is, let me write it down. This is radical form, right? That's radical form. All right. Okay, let's look at the next example. All right, the next example. All right, we have a quotient of two quantities, right? In which the bases are common, right? We have the same base, right? However, this time the operation implied between them is division, and we know by that bar, right, with one quantity at the top and the other quantity at the bottom, right? So what are we going to do when we have that special case? Okay, so we are going to look, to me it looks like letter E, the quotient rule, right? All we do is subtract the exponents, right? So that's what we're going to do here. All right, so we are going to write the number 7 raised to the 1/3 minus 4/3, right? And all we do is the operation implied in the exponents, right? Right here. Okay, so 1/3 take away 4/3, we end up with -3/3, right? But this can be nicely simplified. Okay, so -3/3 is the same as saying -1, right? But we are required to write this using positive exponents. But this doesn't look to me like a positive exponent, so this is the same as 1/7. How do we go from here to here? All right, we go from here to there using this rule, letter F, right? The negative exponent rule. See how we combine different properties in one single example, right? Okay, let's call it a day with this example, and let's move on to the next page. All right, so let me highlight X and highlight X. So when we do that, it means that we have the same base, and the operation implied between the two of them in this case will be multiplication. So what do we do when we have multiplication? Well, only add the exponents. In this case, one of the exponents is negative 4/7 plus 6/7. So what do we get when we add these two numbers? Well, -4/7 plus 6/7, we get a total of x to the 2/7. All right, and this would be the final answer if you were asked to do only rational exponent. However, if you were asked to write this using radical notation, keep in mind that the index comes from the number I'm highlighting, the denominator of the rational exponent, which is in this case a 7. So we will have the 7th root of x squared. All right. Okay. All right, let's have a look at letter E. Yes, things are starting to get interesting here. All right, this one looks huge, looks big. We are going to apply a few properties at a time. All right. Let me look. Okay, the thing that really stands out to me is the following. These five, right? These five that affects the fifth power that affects the 2, affects the x to the 2/5, and affects the y to the negative 1/3. All right. So in this case, let me go back to this rule, right? I'm thinking of letter C, right? Right. Well, letter C, it's a property given, right, to the product of two quantities to the raised to the n power. You can distribute the powers, right? But this can be extended, right, to, for example, A, B, C, D, right? Even more factors. All we do is A to the n times B to the n, C to the n, and D to the n, right? So we are going to do the same for this example, right? This is what I'm going to do, and I'm going to use different colors, okay? So I'm going to raise the 2 to the fifth power, right? I'm going to circle to color code, and then the quantity x to the 2/5 to the fifth power, all right? And then times the quantity y to the negative 1/3 to the fifth power, all right? So what am I doing essentially? I'm distributing the power to every single factor, all right? The denominator of this will remain the same, x squared y, right? It's going to remain like that. Okay, so let's evaluate one at a time, okay? 2 to the fifth power, it's going to give us a total of 32, right? And then in this case, what do we have? We have the power of another power. What are we going to do with these powers, right? Let me show you here. What are we going to get? So we are going to multiply 2/5 times 5, but this is the same as 5 over 1. In this case, notice these 5s are going to go away. We are going to get at the 2 only, right? So x squared, right? So, and in this case, I'm going to multiply the negative 1/3 times 5. Okay, let me write it down here. Negative 1/3 times 5, but this is the same as saying 5 divided by 1. And this is going to give us negative 5/3. All right. So that's for x and that's for y, right? Y to the negative 5/3. The whole thing right here divided by x squared y. All right. Let's notice something interesting here. Notice how this x squared divides out that x squared. Remember that from rational expressions, right? Simplifying rational expressions. All right. So that's going to give us a 32 y to the negative 5/3, right? And then divided by y, all right? Now I'm going to focus on the y's that remain there, all right? Let's look at this, let's use yellow. So y to the negative 5/3, right? Let me actually write it different so it looks like an actual power. So negative 5/3, all right? Now it looks more like a power, not like a difference, all right? So when I look at this, y to the negative 5/3 raised to the y to the first power, essentially, right? We're going to use the quotient rule in which we subtract the exponents, right? So we are going to write 32 raised to the y minus 5/3 minus 1, right? Okay, let me rewrite this in a different way. 32 divided by negative 5/3 and then minus 1 over 1, which is the same as adding the missing factor 3/3, right? Because in this case, as you notice, we don't have the same denominator. We cannot add the fractions together if we don't have the same denominators, right? So we're going to have 32 raised to the negative 5/3 minus 3/3. That is the same as saying, oh, I'm missing the y. Not 32. I was missing the y right here, right? Okay, so this will be 32 y to negative 5/3 minus 3/3. That's going to give us negative 8/3, right? However, we need to write this using positive exponents. So that negative exponent, it's not okay there, right? Let me write this nicely. Okay. So this will be 32 divided by y to the 8/3, all right? And this is the final answer using rational exponents. If the question was to write it using radicals, it will be 32 divided by y, no, not y, we would use the index of the radical. So the index of the radical comes from the denominator of the rational exponent again. So this will be the cube root of y to the 8th power. Okay, so that's one example, right, in which we applied a good number of properties at a time, right? Okay, let's look at another example, letter F. For letter F, we are going to use the distributive property, right? So for letter F, distribute and distribute. Okay, so what are we going to get initially? So initially we are going to get z to the 2/3 times z to the 1/3. All right, minus, because of the minus in between, z to the 2/3 times z to the 5th power. All right. Okay, in both terms, notice we have two terms. We have this one term and we have this another term, right? So two terms total. We're gonna use the product rule, right? Because we are multiplying the same base, right? And all we do is add the exponent. So what are we gonna get? So z to the 2/3 plus 1/3 minus z to the 2/3 plus 5. But that 5 is the same as saying 5/1, right? This one right here that I'm going to highlight. This 5 right here, it's the same as saying 5/1. And that's going to be useful when it comes to coming up with a least common denominator to add up the powers, right? Okay, so let me add those missing factors, right? 3 and 3. And let's keep going down here. So I'm going to combine 2/3 plus 1/3, right? That's going to give us a total of 3/3. thirds minus z to the 2 thirds plus 5 times 3 is going to give us 15 thirds, right? So this will be, okay, the first term, notice I'm going to simplify the first term. Okay, z to the 3 thirds, that's going to give us z to the first power, right? That reduces to 1 minus, adding these two powers together, we get z to the 2 thirds plus 15 thirds, that's 17 thirds, right? Okay, let's simplify. Okay, so actually we don't need to write this one right there. That's enough, that's fine. And hold on a second. All right. And this would be the final answer if we were required to use only rational exponents. However, using radical form, well, z is just z and the cube root of z to the 17th power. All right, let's call it a day here. All right, let's look at another example, a couple examples ago, right? Let's see. So we are going to FOIL this out. 1/3 x to the 1/3 times itself, x to the 1/3 is going to give us, okay, let's write it down as x to the 1/3 times x to the 1/3. And then plus 2 times the quantity x to the 1/3, right? And then let's change color. -5 to the times x to the 1/3. We multiply those two together. We get -5x to the 1/3. And finally, -5 times +2. That's going to give us a -10. All right. Okay, let's simplify these guys together. Okay, let's see. Number 1. Notice we have the same base, right? And we have multiplication in between them. What do? We are going to, oops, erase everything. We are going to add the exponents together. X to the 1/3 plus 1/3, all right? And then notice something. Notice this guy right here, right? These are like terms, right? How do we know they are like terms? Remember, like terms have the same variables and raised to the same exponents, right? So that's why we can subtract 5 from 2 to get okay, something's going on here, something's weird. Okay, and that one. Oops. Okay, so that's going to give us -3x to the 1/3. And then just -10, just bring it over. And finally, just add up these powers, right? That's going to give us x to the 2/3 minus 3x to the 1/3 minus 10. All right. And letter H, oh, huge, right? This is H of huge, all right? Looks huge, why not? Or what would be your first impression? You look at this and you would say something like, holy guacamole. Right? How about that? Much better? Holy guacamole. What are we going to do here, right? No, not guacamole. No, we're not doing guacamole here. All right. Okay. So we are going to have what we know as nested radicals. What is a nested radical? So it's a radical inside another radical, inside another radical, inside another radical, and so on and so forth, right? So let's start inside out. So the first radical, notice, has an index 4. So I'm going to write x to the 1/4, right? That's x to the 1/4. And then keep in mind the following index right here is an invisible 2. There's another invisible 2 there. Okay? So that whole thing will be raised to the 1/2, right? And then to the 1/3. To the 1/3, right? And then to the 1/2 again. And then to the 1/5. And then finally to the 1/4. Yes, see, they also call it the Wi-Fi signal problem, right? Do you see the shape right here? It looks like the Wi-Fi signal, right? So that's a nickname it has. 1, 2, 3, 4, 5, 6. All right, 5. All right, that's enough. Okay, what are we going to do here ultimately? All right. So you'll realize it is not as bad as it looks. It just looks ugly at first glance. Yes, I agree. But computational wise, it's not going to be that bad because, well, we are going to have the power of another 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 power. What do we do with the power of another power? Just multiply the power. So when we multiply 1 times 1 times 1 times 1 times 1 times 1, what are we going to get? We're going to get 1. And the denominator, 4 times 2, which is 8. 8 times 3, which is 24. 24 times 2, which is 48. 48 times 5, which is 240. And 240 times 4, which is 960. All right? And that'll be final answer. Or the 960th root of x. And there you go. All right. So otherwise, if you want to go from here straight to that answer, all we do is multiply the numbers. 4 times 5, which is 20. 20 times 2, which is 40. 40 times 3, which is 120. 120 times 2, which is 240. 240 times 4, which is no other than 960. And just multiply numbers. That's all it is at the end, all right? Okay, let's move on to the next page, to the very last topic. So we are going to use rational exponent to simplify radical expressions. So that is, we are going to be given, notice something, let's highlight these guys right here. We are going to have the 8th root, the 6th root, the 6th root again, right? And what do we do in this case? We are going to do the following. We are going to turn 8th root or 6th root into smaller roots, all right? So let's see. Number 1, we are going to use, as the title says, use rational exponents to simplify. Okay. By using rational exponents, again, identify the index. The index will be the denominator of the rational exponent. So this will be x to the 4/8, right? But what do we mean by using rational exponent to simplify rational expressions? So we turn into a rational exponent, and that rational exponent turns out that we can write it in lowest terms, right? In this case, x to the 4 over 8 is the same as 1/2. That's x to the 1/2. And then from here, let's go back to radical exponent, to radical notation. In this case, the denominator tells us the index of the radical. In this case, the square root. Okay, square root of x. All right. So what did we get? Okay, let me show you. So notice we have a radical expression here and then another radical expression. They are both radicals. However, both radicals here, one of them has more complicated powers and indices, and the other one has simpler powers and indices, right? So that's what we're doing. All right. What about letter B? For letter B, okay, we are going to have 25, the sixth root of 25. The sixth root of 25, notice that 25 has an invisible 1 as a power, right? So let's do the following. Number 1, this will be 25 to the 1/6 power. All right, then you may argue here, well, how can we simplify this? This one right here looks like we're in dead ends, right? However, we're not necessarily in dead end right here. Let me show you something. This number 25, right? The number 25 can be rewritten as 5 to the 2nd power, right? And keep the outermost power, right? The outermost layer power, which is 1/6. And then from here, notice we have the power of another power. What do we do with the powers again? We multiply the power. So 5 times, okay, let me multiply this on the side, 2 times 1/6, and in this case, this is the same as saying 2 over 1, right? This is going to give us 2/6. But 2/6 reduces to 1/3. So what are we going to get here? 5 to the 1/3. That's the rational exponent in lowest terms. Let's go back to radical form, right? So we are going to have the cube root of 5. Okay, let's compare. We were given an ugly, a big index with large number inside. We were able to simplify to a radical with a smaller index and a smaller number inside of the radical, all right? Okay, let's do the same for the next example, all right? The next example, so we have r squared s to the 4th power, the whole thing, okay, the whole thing to the 1/6, right? And that's because this is the index of the radical, right? Again, the index of the radical tells us the denominator of the rational exponent, right? Okay, so from here, what are we going to do? From here, we're going to use that property of exponents in which we distribute the exponent, right? We distribute the exponents to get the following. So let's see. We're going to have r to the 2 times 1/6 times s to the 4th times 1/6, right? Okay, so in this case, we have product 2 over 1, right? That's the same as saying 2 over 1, and that's the same as saying 4 over 1. Okay, so let's keep going with this. So we're going to multiply these two fractions together. 2 over 1 times 1 over 6, that's going to give us 2 over 6 times s raised to the 4 over 1 times 1 over 6. That's going to give us 4 over 6. Okay, so from here we are going to simplify this fraction to lowest term and that fraction as well to lowest terms. Okay, let's see. So 2/6 reduces to 1/3, right? And let me highlight this just so you can see where is this coming from, right? And let me indicate with an arrow where does it go to, right? The power of s, which used to be 4/6, reduces to 2/3, all right? And I'm going to highlight this using orange, all right? And I'm going to point it out with the same color, orange, right? Okay, notice something interesting here, right? I would like you to observe what these two exponents have in common. These two exponents have the denominator in common, right? And let me do something on the side. When I have, for example, 1/7, this is the same as 1 times 1/7. So basically, I'm doing the multiplication backwards, right? When I have 1/5, this is the same as 1 times 1/5, right? Why is that possible, right? Okay, for the first case, this is 1/1. So that's 1 times 1. That's going to give us back the 1 right here. And then in the denominator, the 1 times 7, it's going to give us the 7 right here. On the other example, 1 times 1, it's going to give us a 1. 1 times 5 is going to give us a 5. 1 times 5 equals 5. So I'm going to do the same over here. 1/3 is the same as saying r to the 1 times 1/3 times s to the 2/3, which is 2 times 1/3, right? And I will still highlight that common power right here. Okay, why am I doing that? Because I'm going to do the reverse of what I'm highlighting here, right? So on the quantity I was highlighting at the beginning of the exercise, right? I was distributing the power to the other powers, right? To each of the powers inside of the parentheses. Now I'm going to do this backwards. I'm going to undistribute, right? This one, for example. Okay, let me see if I have space here. Okay, let me see if I can scroll to the right. Yes, I'm gonna do it outside. You do it below the paper on your space, right? So I'm going to undistribute the power r to the first times s to the 2. The whole thing to the 1/3, right? This is the same as if I distributed 1/3 times 1, right? Which is this guy right here. And 1/3 times 2, which is the same as this guy right here, right there. All right. Okay, so this is what we end up with, right? R to the first times rs to the second. That's the same as just r. Just rs squared raised to, well, not raised, well, yes, raised to the 1/3, right? But this is the same as saying the cube root of rs squared. All right, what did we get? We get a smaller index and smaller powers inside, right? We used to have bigger index, bigger power. So that's the idea. Have with large and start with large numbers, end up with smaller powers and smaller indices. Okay. Okay, let's do another one. All right, square root of x times the fourth root of x. Okay, so number one, let's start by writing square root of x as x to the 1/2 and the fourth root of x as x to the 1/4. Okay, now because we have the same base but raised to different powers, all we do is, because in addition to that, the operation between the two of them is multiplication, so add 1/2 plus 1/4. And notice again the space I'm leaving in between the two fractions. I will need that space to add those missing factors, right? So we're going to end up with x to the 3. Oh, wait a minute, not 3. The missing factors looks like I got it wrong. Okay. Nothing happened. Whatever you saw earlier, it wasn't a mistake. It was your imagination. All right. Okay. Yeah. It was just a dream. Okay. So x to the 2/4 plus 1/4. Okay. So 2/4 plus 1/4. That's x to the 3/4. Right. And what are we going to get here? The fourth root of x to the third power. Okay, again, keep in mind that the denominator of the rational exponent is the same as the index of the radical. All right? Let's do another one very similar. All right. So in this case, letter E is going to be very similar to letter D, right? Do you see the similarities right here? This is a product and this is a quotient. We are going to do exactly the same process, but we are going to apply the laws of exponent that instead of a plus, we're going to minus the exponent. So let's see how it's not going to work. So we're going to write, let's start by writing x to the 1/2 divided by x to the 1/3. Okay, so what are we going to do? X to the 1/2, okay, x to the 1/2 minus 1/3. Okay, notice again the gap. So in this case, we need an LCD, 3 and 3, 2 and 2, because the least common denominator is the number 6, right? So we are going to have x to the 3/6 minus 2/6. And if we subtract these two exponents, 3/6 minus 2/6, we are going to get x to the 1/6, right? Yes. And this is the same as the 6th root of x. Okay, the 6th root of x. All right. Okay. For letter F, we're going to be doing some sort of the backwards thing. So instead of making something simpler, we are going to turn something that looks simple-ish, and we are going to turn it into a single radical, but this will have very, very, very weird looking numbers and indices. You'll see. So this one is going to take a while. All right. So what did we do here? Okay. In these cases, we had, notice, okay, let me use letter D as a reference, right? What do we do here? So in this case, we have the exact same base, right? X. What do we do with the exponents? Well, doesn't matter if they're not the same. All we do is adding them, right? That's what we did here. But that happens only when these x's, these bases are the same, all right? However, it's not going to be the same case for letter F, and I'll show you why. Okay, number one, let's start by writing the number cube root of 3 as 3 to the 1/3, right? And then that times 2 to the 1/2, right? In this case, the reason why, okay, notice we have, first of all, notice we have multiplication implied, right? Just like example did that I did as a reference, right? In this case, we cannot just add the exponents because the bases are not the same. If these were both the number 3, well, then we can do that. Or if they were both the number 2, then we can still do that, but not in this case. So what are we going to do in this case? Well, the trick here is, well, we wish we have the same denominator, so we can do the trick of undistribute and then write it as a single radical. We don't have it. We don't have the same denominator for each power, but we can make that happen. So let's multiply this guy by 2 and multiply this by 3. All right. So this will be 3 to the 2/6 times 3/6. Okay. Now, what are we going to do from here? Again, keep in mind that the power right here, 2 divided by 6, is the same as saying 3 to the 2, and I'm going to use a different color here, 2 to the times 1/6. And same here, right? 3 divided by 6 is the same as saying 2 to the 3 times 1/6, right? How is this going to be useful though? All right, so I'm going to use the distributive properties, right? And I'm going to factor out this 1/6, right? Like if I were distributing to some term and then the other term, right? Which is ultimately going to be going back to this and that, right? Okay, let me use a different highlighter. Okay, this and that. Okay, so what are we going to get here? Okay, so we are going to end up with 3 to the 2nd power times 2 to the 3rd power. Okay, if we were distributing this, okay, we get 2 times 1/6, which is this 2 times 1/6, which will become 2/6, right? If we distributed 1/6 times 3, this is 3 times 1/6, which reduces to 3/6, right? Now, the quantity inside of the rational power will be, okay, number 1, 3 to the 2nd power. That's going to be a 9 times 2 to the 3rd power, which is 8 raised to the 1/6. And that's going to be 72 raised to the 1/6. And let's write this into radical form. That's the 6th root of 72. Okay, and that's final answer. And this is likewise the last example for this section 7.2. So, and I'll see you in the next video on 7.3. Okay.